Good morning, everyone. I am Rochelle E. Cabison, and I will be the next discussant for today. I will be discussing the remaining basic theorems on congruences. To start, let me introduce to you to the objective of this lesson. At the end of the lesson, you will be able to state and apply the basic theorems of the modular congruence relation. Determine the unit digit of an integer raised to another integer using congruences. And lastly, determine the last two digits of an integer raised to another integer using congruences. Before we proceed to the remaining theorems, let's have a short recap. As what Ms. Bonto discussed, by definition, A is congruent to an integer b modulo m if m divides A minus b. Moreover, Theorem 1 states that A is congruent to B mod M if and only if A is equal to B plus K times M for some integer K. Next, by reflexive property, A is congruent to A mod M. Additionally, by symmetric property, if A is congruent to B mod M, then B is congruent to A mod M. Lastly, by transitivity, if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. Note that some of these theorems will be used in proving the theorems that I am about to discuss. Let's proceed. Theorem 3 states that A is congruent to B mod M if and only if A and B leaves the same remainder when divided by M. To prove this, suppose that A is congruent to B mod M. Then by theorem 1, we say that A is equal to B plus K times M for some integer K. Supposing that we divide B as well by some integer M. Then, by division algorithm, we say that B is equal to M times Q plus R, where R is greater than or equal to 0 but less than M. Then, by substitution, we will have A is equal to M times Q plus R plus K times M. Then, regrouping terms, we will have M times Q plus K plus R, which shows that whenever we divide A by integer M, it will leave the same remainder R. End of proof. To show that this theorem is true, let's have some numerical example. 48 is congruent to 28 mod 5. This example shows that theorem 3 is true, since 48 and 28, both of it, when divided by 5, leaves the same remainder, which is 3. Additionally, when 29 and negative 3 are divided by 8, the remainders are the same. So, by theorem 3, we say that 29 is congruent to negative 3 modulo 8. Consequently, by theorem 3, we have this corollary, which states that the integer r is the remainder when a is divided by m, if and only if a is congruent to r mod m, where r should be greater than or equal to 0 but less than m. By this corollary, every integer a is congruent to its remainder r modulo m. Thus, r is called the least residue of A modulo M. To elaborate this, let's have some examples. The least residues of 22, 4, and negative 2 modulo 5 are 2, 4, and 3 respectively, since 22 is congruent to 2 mod 5, 4 is congruent to 4 mod 5, and negative 2 is congruent to 3 mod 5. 2, 4, and 3 are called the least residue since these are the smallest integers that will be the remainder when 22, 4, and negative 2 is divided by 5 respectively. Notice that the residues are less than the modulus. Hence, given modulo m, the residue r should always be greater than or equal to 0 but less than m. To discuss this, let's proceed to the next slide. A set of m integer is a complete set of residues modulo m if every integer is congruent modulo m to exactly one of them. To discuss this, let's have some examples. A set -8, 13, 2, 27 is a complete set of residues modulo 4 since -8 is congruent to 0 modulo 4, 13 is congruent to 1 modulo 4, 2 is congruent to 2 modulo 4, and 27 is congruent to 3 modulo 4. As you can see, the residues that we have here are 0, 1, 2, and 3, which satisfies the condition that r should be greater than or equal to 0, but less than or equal to our m. Observe as well that the residues that we have in our examples seems to be integers. Thus, it follows that the set of integer z can be partitioned into m non-empty pairwise disjoint classes called congruence classes modulo m. To elucidate this, let residue r denote the set of integers that have r as their least residue modulo m. To cite some example, let's take a look on the various classes of modulo 5. Below are the various congruence classes modulo 5. This is read as residue 0 class modulo 5. These are the set of integers that when we divide by 5 will leave a remainder of 0. Thus we have -10, -5, 0, 5, 10, and many other integers that when we divide by 5 will leave a remainder of 0. Generally, if we are going to determine all of the integers that when we divide by 5 will leave a remainder of 0, we may follow the formula 5q, where q is an element of integer. Next, we have this residue 1 class modulo 5. Same goes here. These are the set of integers that when divided by 5 will leave a remainder of 1. To give sum, we have -9, -4, 1, 6, 11, and many other numbers that will leave a remainder of 1 when divided by 5. Generally, if we are going to determine all of the integers that will leave a remainder of 1 when divided by 5, we may follow this formula. 1 plus 5q, where q is an element of integer. Next, we have residue 2 class modulo 5. Same goes here. These are the set of integers that will leave a remainder of 2 when divided by 5. To give sum, we have -8, -3, 2, 7, 12, and many other integers that will leave a remainder of 2 when divided by 5. Generally, if we are going to determine all of the integers that will leave a remainder of 2 when divided by 5, we may follow the formula 2 plus 5q, where q is an element of integer. Next, we have this residue 3 class modulo 5. Same goes here. These are the set of integers wherein if we are going to divide it by 5, it will leave a remainder of 3. To give sum, we have -7, -2, 3, 8, 13, and many other numbers that will leave a remainder of 3 when divided by 5. Generally, if we are going to determine all of the numbers that will leave a remainder of 3 when divided by 5, we may use this formula 3 plus 5q, where q is an element of integer. Lastly, we have residue 4 class modulo 5. Same goes here. These are the set of integers that when divided by 5 will leave a remainder of 4. To give sum, we have -6, -1, 4, 9, and 14. And of course, many integers that when we divide by 5 will leave a remainder of 4. Generally, if we are going to determine all of the integers that will leave a remainder of 4 when divided by 5, we may use the formula 4 plus 5q, where q is an element of integer. We are going to stop in determining the class's modulo 5 since we reach 4 here to be able to satisfy the condition that your residue should be greater than or equal to 0 but less than your modulus 5. So generally, to determine the congruence class's modulo m, we may refer to this formula. So again, this is read as residue A class modulo m, and to be able to get all of the integers for these classes, we may follow A plus m times q, where q is an element of integer. Notice that the classes that we determined showed a specific set of numbers which are integers. Thus, we may say that these classes are non-empty, pairwise disjoint, and their union is the set of integers. Accordingly, these classes form a partitioning of the set of integers as shown in the figure 1. The least residues 0, 1, 2, 3, 4 serve as representatives of the classes 0, 1, 2, 3, and 4 respectively. To continue, let's take a look on theorem number 4. Theorem 4 states that if AC is congruent to BC modulo M and the GCD of C and M is D, then A is congruent to B modulo M divided by D. To prove this, since AC is congruent to BC modulo M based on theorem 4, then by definition, we say that M divides AC minus BC or M divides C times A minus B. Since it is also stated that the GCD of C and M is D, it follows that M divided by D divides C divided by D times A minus B. Moreover, based on theorem number 7 on GCD, we say that M divided by D and C divided by D are relatively prime, thus their GCD is equal to 1. Lastly, by Euclid's lemma, which states that if A and B are relatively prime and A divides BC, then A divides C. It follows that M divided by D divides A minus B. Thus, theorem 4 is true and A is congruent to B modulo M divided by B. End of proof. To give some examples, we are going to proceed with our next slide. Verify that 8 times 37 is congruent to 8 times 7 modulo 12. To show that theorem 4 is true, we are going to get the GCD of 8 and 12. Getting it, we are going to have the GCD of 8 and 12, which is 4. Then, from our original expression, we are going to cancel out our 8 from both sides. Thus, we have 37 is congruent to 7 modulo 12 divided by 4. Simplifying it further, we have 37 is congruent to 7 modulo 3, which is true since 12 divided by 4 divides 37 minus 7. Simplifying it, we have 3 divided by 37 minus 7. Verify that 6 times 92 is congruent to 6 times negative 4 modulo 32. To prove this, we are going to get the GCD of 6 and 32. Hence, the GCD of 6 and 32 is 2. Then, we are going to do the same process as earlier, remove 6 from both sides of our expression. Thus, we have 92 is congruent to negative 4 modulo 32 divided by 2. Simplifying it further, we have 92 is congruent to negative 4 modulo 16. Thus, this is true since 32 divided by 2 divides 92 minus negative 4. Simplifying it, we have 16 divides 92 minus negative 4. To continue, let's have our last theorem, which is theorem number 5. Theorem 5 states that if A sub I is congruent to B sub I modulo M for I is equal to 1, 2, 3 to n, then the following statements are true. The sum of A sub I from I is equal to 1 to m is congruent to the sum of B sub I from I is equal to 1 to m modulo m. And the product of A sub I from I is equal to 1 to m is congruent to the product of B sub I from I is equal to 1 to m modulo m. To show that this theorem is true, let's cite some examples. Find the remainder when 67 raised to 68 is divided by 63. To answer this, we need to determine the cycle of base 67 modulo 63 until we get a remainder of 1. To start, we have 67 is congruent to 4 modulo 63. Since if we divide 67 by 63, the remainder will be 4. Raising both sides of our expression by 2, we will have 67 squared is congruent to 4 squared modulo 63. Simplifying it, we will have 67 squared is congruent to 16 modulo 63. Therefore, if we divide 67 squared by 63, it will leave a remainder of 16. Next, raising both sides by 3, we will have 67 cubed is congruent to 4 cubed modulo 63. Simplifying it, we are going to have 67 cubed is congruent to 64 modulo 63. Taking a look on the residue, it didn't satisfy that the residue should be greater than or equal to 0 but less than n. Therefore, simplifying it further, we will have 67 cubed is congruent to 1 modulo 63. Since the remainder is already 1, we are going to use this fact to be able to solve our problem. Let's proceed to the next slide to continue. To continue our solving, we need to express 67 raised to 68, wherein we have 67 raised to 3, because 67 raised to 3 will leave a residue of 1 whenever divided by 63. Thus, we have 67 raised to 68 is equivalent to 67 raised to 3 raised to 22 times 67 squared. Applying the properties of congruences, we have 67 cubed raised to 22 times 67 squared is congruent to 1 raised to 22 times 16 modulo 63. Simplifying it further, we will have 67 cubed raised to 22 times 67 squared is congruent to 16 modulo 63. Hence, the remainder, when 67 raised to 68 is divided by 63, is 16. Let's have another example. Find the remainder when 123 raised to 456 is divided by 5. We are going to do the same process as what we did earlier. First, we need to find the cycle of base 123 modulo 5 until we get a remainder of 1. First, we have 123 is congruent to 3 modulo 5. Since if we divide 123 by 5, it will leave a remainder of 3. Squaring both sides of our expression, we will have 123 squared is congruent to 3 squared modulo 5. Simplifying it, we have 123 squared is congruent to 9 modulo 5. Since the residue did not satisfy the condition that our residue should be greater than or equal to 0 but less than 5, we are going to have 123 squared is congruent to 4 modulo 5. Since whenever we divide 123 squared by 5, the remainder will be 4. Cubing both sides of our expression, we will have 123 cubed is congruent to 3 cubed modulo 5. Simplifying it, we have 123 cubed is congruent to 27 modulo 5. Simplifying it further, we will have 123 cubed is congruent to 2 modulo 5. Next, raising both side by 4, we will have 123 raised to 4 is congruent to 3 raised to 4 modulo 5. Simplifying it, we will have 123 raised to 4 that is congruent to 81 modulo 5. Simplifying it further, we will have 123 raised to 4 is congruent to 1 modulo 5. As you can see, in this expression, we have our residue that is 1. Therefore, we are going to use this fact to be able to solve our problem. To continue, let's proceed to the next slide. We are going to use the same process as what we did in the first example. To be able for us to solve this problem, we need to express 123 raised to 456 in a way that we have 123 raised to 4. Since 123 raised to 4 when divided by 5 will leave a remainder of 1. Thus, we will have 123 raised to 456 is equivalent to 123 raised to 4 raised to 114. Applying the properties of congruence, we will have 123 raised to 4 raised to 114 is congruent to its residue 1 raised to 114 modulo 5. Simplifying it further, we will have 123 raised to 4 raised to 114 is congruent to 1 modulo 5. Hence, we say that the remainder when 123 raised to 456 is divided by 5 is 1. At this point, we are going to look at the application of the properties of congruences in finding the last digit of an integer which is raised to another integer. For example number 1, find the last digit of 3 times 7 raised to 2012 plus 4 times 3 raised to 2011. In this kind of problem, we are going to take a look at those integer that is being raised to another integer. In this case, we have 7 raised to 2012 and 3 raised to 2011. Now, we are going to do the same thing as what we did earlier, but take note that we are asked to get the last digit. Therefore, it also means that we are going to get modulo 10. Therefore, we need to determine the cycle of base 7 modulo 10 until we get a remainder of 1, and the cycle of base 3 modulo 10 until we get a remainder of 1 as well. To start with, 7 is congruent to 7 modulo 10, since whenever you divide 7 by 10, it will leave a remainder of 7. Again, applying the rules of congruences, we will have 7 squared is congruent to 7 squared modulo 10. Simplifying it, we will have 7 squared is congruent to 49 modulo 10. And 7 squared is congruent to 9 modulo 10. Since the residue is still not 1, we need to proceed further. 7 cubed is congruent to 7 cubed modulo 10. Thus, 7 cubed is congruent to 343 modulo 10. And 7 cubed is congruent to 3 modulo 10. Still the residue is not 1, proceed with the next power. 7 raised to 4 is congruent to 7 raised to 4 modulo 10. Simplifying, we have 7 raised to 4 is congruent to 2401 modulo 10. Simplifying it further, we will have 7 raised to 4 is congruent to 1 modulo 10. Therefore, if we divide 7 raised to 4 by 10, it will leave a remainder of 1. Since we have a residue of 1 here, this is the fact that we are going to use to be able to solve our problem. Hence, we are not yet done, since we have 3 raised to 2011. Therefore, we need to determine the cycle of base 3 modulo 10 until we get a remainder of 1 as well. To start with, we have 3 is congruent to 3 modulo 10. Still not 1, proceed with the next power. 3 squared is congruent to 3 squared modulo 10. Simplify, we have 3 squared is congruent to 9 modulo 10. Still not 1, proceed with the next power. 3 cubed is congruent to 3 cubed modulo 10. Expanding it, we will have 3 squared is congruent to 27 modulo 10. Simplifying, we have 3 cubed is congruent to 7 modulo 10. Still not 1, proceed with the next power. 3 to the 4th is congruent to 3 to the 4th modulo 10. 3 to the 4th is congruent to 81 modulo 10. Simplifying it, we will have 3 to the 4th is congruent to 1 modulo 10. Since we have a residue of 1 when 3 to the 4th is divided by 10, therefore, this is the fact that we are going to use to be able to solve our problem. Let's proceed to the next slide to be able to solve our problem. Continue, we need to express our 7 raised to 2012 and 3 raised to 2011 in a way that we have 7 raised to 4 and 3 raised to 4 as well. Thus, we have 3 times 7 raised to 2012 plus 4 times 3 raised to 2011, which is equal to 3 times 7 raised to 4 raised to 503 plus 4 times 3 raised to 4 raised to 502 times 3 cubed. Applying the properties of congruences, we have 3 times 7 raised to 4 raised to 503 plus 4 times 3 raised to 4 raised to 502 times 3 cubed is congruent to 3 times 1 raised to 503 plus 4 times 1 raised to 502 times 7 modulo 10. Simplifying this part of our expression, we will have 3 plus 4 times 7 modulo 10. Simplifying it further, we will have 31 modulo 10. Thus, we have 3 times 7 raised to 4 raised to 503 plus 4 times 3 to the 4th raised to 502 times 3 cubed is congruent to 1 modulo 10. Hence, the last digit of 3 times 7 raised to 2012 plus 4 times 3 raised to 2012 is 1. Let's have another example. For our next example, we need to find the last digit of 7 times 11 raised to 2015 plus 2 times 9 raised to 1025. We are going to apply the same process wherein we are going to determine the cycle of base 11 and base 9 modulo 10 until we get a remainder of 1. To start with, we have 11 is congruent to 1 modulo 10. Since this expression shows a remainder of 1, we are not going to continue further. Proceeding to the base of 9, we have 9 is congruent to 9 modulo 10. Since the remainder is not yet 1, we need to proceed further. Squaring both sides, we will have 9 squared is congruent to 9 squared modulo 10, wherein this expression can be rewritten as 9 squared is congruent to 81 modulo 10. Thus, simplifying, we will have 9 squared is congruent to 1 modulo 10. Since the remainder is already 1, we are going to stop. For the next step, we are going to do the same process as what we did earlier. We need to express 11 raised to 2015 in such a way that we have 11 as the base, and 9 raised to 1025 in such a way that we have a base of 9 squared. To elaborate, we have 7 times 11 raised to 2015 plus 2 times 9 raised to 1025, which can be expressed as 7 times 11 raised to 2015 plus 2 times 9 squared raised to 512 times 9. Applying the properties of congruence, we will have 7 times 11 raised to 2015 plus 2 times 9 squared raised to 512 times 9 is congruent to 7 times 1 raised to 2015 plus 2 times 1 raised to 512 times 9 modulo 10. Simplifying this part of our expression, we will have 25 modulo 10. Thus, we have 7 times 11 raised to 2015 plus 2 times 9 squared raised to 512 times 9 is congruent to 5 modulo 10. Hence, the last digit of 7 times 11 raised to 2015 plus 2 times 9 raised to 1025 is 5. Now, we are going to proceed with finding the last two digits using the properties of congruences. In finding the last two digits using congruences, we may follow the same process as what we did earlier, except that the modulo that we are going to use is 100. For the first example, find the last two digits of 17 raised to 2012. Same goes here, we need to determine a cycle of base 17 modulo 100 until we get a remainder whose ones digit is 1. To start with, we have 17 is congruent to 17 modulo 100. Since the ones digit of the remainder is not 1, we need to proceed with the power of 2. 17 raised to 2 is congruent to 17 raised to 2 modulo 100. 17 raised to 2 can be expressed as 289. Hence, we have 17 squared is congruent to 89 modulo 100. Since the ones digit of our remainder is not 1, we need to proceed to the next power, which is 3. 17 cubed is congruent to 17 cubed modulo 100. 17 cubed can be expressed as 4,913. Hence, we have 17 cubed is congruent to 13 modulo 100. Since the ones digit of our remainder is not 1, we need to proceed with the power of 4. 17 raised to 4 is congruent to 17 raised to 4 modulo 100. 17 raised to 4 can be expressed as 83,521. Hence, we have 17 raised to 4 is congruent to 21 modulo 100. Since the ones digit of our remainder is already 1, we are going to stop and we are going to use this fact to solve our problem. To continue, let's proceed to the next slide. Since the remainder wherein the ones digit is 1 appeared in 17 raised to 4, we need to rewrite 17 raised to 2012 in a way that we have 17 raised to 4. Thus, we have 17 raised to 2012 is equal to 17 raised to 4 raised to 503. Applying the properties of congruences, we have 17 raised to 4 raised to 503 is congruent to 21 raised to 503 modulo 100. Rewriting 21 raised to 503, we will have 17 raised to 4 raised to 503 is congruent to 21 raised to 5 raised to 100 times 21 raised to 3 modulo 100. We rewrite 21 raised to 503 in this way since 21 raised to 5 when divided by 100 will leave a remainder of 01. Thus, we have 17 raised to 4 raised to 503 is congruent to 01 raised to 100 times 61 modulo 100. Simplifying this part of our expression, we have 17 raised to 4 raised to 503 is congruent to 01 times 61 modulo 100. Thus, we have 17 raised to 4 raised to 503 is congruent to 61 modulo 100. Hence, the last two digits of 17 raised to 2012 is 61. Let's have another example in the next slide. For the last example, find the last two digits of 23 raised to 2011. We are going to do the same process as what we did earlier, wherein we need to determine the cycle of base 23 modulo 100 until we get a remainder whose ones digit is 1. To start with, 23 is congruent to 23 modulo 100. Since the ones digit of the remainder is not 1, we need to proceed to the power of 2. 23 squared is congruent to 23 squared modulo 100. 23 squared can be expressed as 529. Thus, we have 23 squared is congruent to 29 modulo 100. Since the ones digit of the remainder is not 1, we need to proceed to the power of 3. 23 cube is congruent to 23 cube modulo 100. 23 cube can be expressed as 12,167. Thus, we have 23 cube is congruent to 67 modulo 100. Still, the ones digit of the remainder is not 1. So, we need to proceed to the next power, which is 4. 23 raised to 4 is congruent to 23 raised to 4 modulo 100. 23 raised to 4 can be expressed as 279,841, wherein we may rewrite it as 23 raised to 4 is congruent to 41 modulo 100. Since the remainder, which is 41, its ones digit is 1, we may now use this fact to be able to solve our problem. To continue, let's proceed to the next slide. Since the remainder whose ones digit appeared in 23 raised to 4, we need to express 23 raised to 2011 in which we have 23 raised to 4. Thus, we have 23 raised to 2011 is equal to 23 raised to 4 raised to 502 times 23 raised to 3. Applying the properties of congruences, we have 23 raised to 4 raised to 502 times 23 raised to 3 is congruent to 41 raised to 502 times 67 modulo 100. Rewriting 41 raised to 502, we will have 23 raised to 4 raised to 502 times 23 raised to 3 is congruent to 41 raised to 5 raised to 100 times 41 squared times 67 modulo 100. We expressed 41 raised to 502 in this way since 41 raised to 5 will leave a remainder of 01 when divided by 100. Simplifying this part of our expression, we will have 23 raised to 4 raised to 502 times 23 raised to 3 is congruent to 01 raised to 100 times 81 times 67 modulo 100. Simplifying it further, we have 23 raised to 4 raised to 502 times 23 raised to 3 is congruent to 5,427. Since we are after with the last two digits, we have 23 raised to 4 raised to 502 times 23 cubed is congruent to 27 modulo 100. Hence, the last two digits of 23 raised to 2011 is 27. Once again, I am Rochelle E. Cabison. Thank you for listening and have a great day.